notes shortly on Canvas for both today and yesterday. Dr. Rahman, take over.
Yeah, thanks. Thanks a lot, sir. So please allow me just a minute just for the setup part.
Sure.
I hope my
Sure.
this display is visible, right?
Yes, your notes are visible.
Yeah, thanks. So welcome everyone and a very good afternoon. And yesterday we started the quantum, sometimes this digital board again today. Yesterday also it had certain problems. Just allow me 1 or 2 minutes because normally I do everything in chalk and talk mode. So I need these things. Yeah, thanks. So quantum information theory, we started yesterday, and certain things we have seen, right? Especially what is density matrix, some background on the, especially the noiseless quantum theory, and some part of the noisy quantum theory a bit, not much. But today I'll cover mainly two aspects. So one is the quantum channel part, but quantum channel also needs certain prerequisites, especially I'll discuss on noisy quantum channel. It also needs certain prerequisites that I'll cover. And secondly, we'll discuss on one important aspects in quantum communication, quantum information, that's called no cloning theorem. Right. So before we start, we start the formally the quantum channel and various quantum channels and all. We need some background. Although I believe that many of you already know what is the composite quantum system entangled state, but still I'm covering 5-10 minutes on these things so that those who are new, they can feel comfortable to the subject. So one is the something called a composite quantum system. So far, what we have learned basically individual quantum systems like a Kate psi, that how we could represent by alpha Kate 0 and beta Kate 1, especially how to calculate this probability alpha and beta with the help of measurement operators, mathematical projections, the outer product or the projector operators, and all those things we have seen. Also, we have seen the ensemble description of this, like if the generation of all these states can be noisy, so we can if we have the probabilistic description pi for certain state like Kate psi I, right? And then we defined something called a density matrix as is pi ket psi I outer product with psi I yesterday for many such ensembles ket I, right? For all I, right? So now uh, today we'll see if there are multiple quantum systems that you have taken two qubits, for example, ket0 and ket0, right? Two particular quantum system, and together this forms a composite quantum system, and they are described by a mathematical operator called a tensor product. Tensor product. So tensor product is denoted by this 0, 0, right? So you can write it as either if they are same information. So either you can write the ket0 tensor product with ket0, and also you can write it as 0, 0 this way, right? Both ways, this is possible to write, right? So in general, suppose there are two quantum states, right? Say the first quantum state is psi1 ket, that is equals to say a1 ket 0 plus b1 ket 1, right? And we can also represent that information as a column vector a1 b1 that we discussed yesterday, right? And somebody is saying my voice is not clear. Can anyone else confirm I'm audible properly or not?
Yes, you are
Yeah.
audible.
Yeah. Then those who are facing problem may rejoin. And then we can have a another state, say ket psi 2, that we can represent, say a2 ket 0 plus b2 ket 1, right? So that is, we can also represent in the column vector notation, so a2 and b2, right? So this way we can represent two particular quantum state. Now, when we say a composite quantum system which combines both these two states, right? So it's like something like you cannot add an apple with an orange, right? Similarly, you can simply just by addition, like psi1 plus psi2, you cannot do, right? That way, that may not be a valid quantum state, right? So a better way to say them that makes a composite quantum system, and we will represent a composite quantum system. Suppose this 1 and 2 form a composite quantum system, get psi1 2, this particular state, which is basically a tensor product of psi1 and psi2. Okay. And we can write it as, say, a1 b1 tensor product with, say, a2 b2. Okay. And how to define the tensor product is very simple. Is this is a 2x1 system. This is another 2x1 system, and together it will make a 4x1 system. Okay. And what are the components here and here? So it will be a1 times this entire vector, right? So a1 times this entire vector psi2, and a2 times, b1 times the vector psi2, right? Uh, so it is all together, it looks like this: a1, a2, b2, and b1, a2, b2. So now if you just simply multiply them, it will be a 4x1 vector, right? So what are the components? First one will be a1, a2. Second one will be a1, b2, right? Third one will be b1, a2, and b1, b2. These are the components for the tensor product. Now, of course, we learned it in the state representation form, or the vector representation form of the state, right? So this one is a vector. It's a unit vector, basically, complex unit vector, right? It's a unit vector, complex unit vector. And we know that if there are two vectors, then we can represent their composite quantum system. If there are two such unit vectors, psi1 and psi2, now I can represent it to a bigger, say it has a n cross 1 dimension, it has a n cross another m cross 1, say for example m cross 1 dimension. Then I can form a psi1 2 as a composite system with mn cross 1 dimensional vector, right? It's another vector. Also, we have yesterday defined what is the density matrix, right? So out of it is basically we can form a density matrix. Now, if there is a particular for psi1, the density matrix is suppose, so this belongs to the state psi1. It's a one ensemble description in the density matrix form. And suppose there is another say matrix sigma, right, which is coming from density matrix coming from the state psi2, right? So we can similarly form a composite quantum system in the density matrix form. Of density matrix form. And that one is rho tensor product with sigma, right? So now once it is a matrix tensor product form, so the formula is if there is there are two operators, say for example, two operators are A and B, the components are A11, A12, A21 and A22, and B is B11, B12, B21 and B22. If these are two matrices, they can be density matrix or any other matrix, then the tensor product of A and B will be A11 times the matrix B, okay? A12 times the matrix B, A21 times the matrix B, and A22 times the matrix B. Now you can see, like if it is a 2 cross 2 matrices, these are two matrices of 2 cross 2, it will be a 4 cross 4 matrix, right? So you can augment the dimension. You can see the augmented dimension for the composite system in the tensor product form, right? Whether they are in the vector representation or in the density matrix representations, both side, you can always form a composite quantum system. Now there are certain special gates, that is the gates. So we have seen for the single qubit gate, like the Pauli operators, like the X operator or Pauli X operator as your 0, 1, 1, 0, right? Or the Z operator or Pauli Z operator as your 1, -1, 0, 0, right? So this kind of matrices. So there is a special 2 qubit operators called the controlled gate. So which is a special 2 qubit gates, right? And it basically apply to the composite quantum system, not a single qubit, but it's a composite qubit or 2 qubit system. So the definition is as such that it does nothing. It does nothing if the first qubit is 0. If the first qubit is 0, then it does nothing. It does certain operation if the first qubit equals to 1. Okay. So this is the definition of the controlled gate. And let us take two specific case. One is the C-NOT gate, controlled NOT gate. So a control NOT gate. So by definition, if I have a composite system of two quantum states, say for example, Ket 00, Ket 01, Ket 10, and Ket 11, if these are the four possible state for 2 qubits, right? And I apply a C-NOT gate, controlled NOT gate. By definition, for the first 2 qubits, you can see the first qubit are 00. So there will be no change to the second qubit. So 00 will be 00 and 01 will also be 01. So there will be no change to the first two quantum states. Now, by definition of C-NOT, if the first qubit is 1, it performs NOT operations to the second qubit. Okay. So if the first qubit is 1, that means first qubit is 1. So it does the NOT operation on the second qubit. So the second qubit is what? 0. So it will become 1. Here it is 1, it will become 0. Right? So of course these two states are swapped basically, right? So in a sense that first qubit, if it is 1, then the second qubit we perform the NOT operations, logical operations, right? So what effectively we have done is, if we have a composite quantum state Ket psi, and we define them by alpha 00 plus beta 01 plus gamma 10 plus delta. So this is, suppose this is gamma, and this is delta 1 1, right? So gamma 1 0 and delta 1 1. And if I perform the C0 gate, what I get is alpha 0 0 plus beta 0 1. These two are unchanged. But here I have a swap, and I will be effectively getting delta 1 0 plus gamma 1 1, right? So in the vector notation, what will happen in the tensor product form? So my initial quantum state was alpha, beta, gamma, and delta. This was my initial state. And if I apply the C naught gate in the tensor product form, so I'll be getting alpha, beta, and delta and gamma, right? So this is the purpose of NOT gate, control NOT gate, where it like it performs a control to NOT operations on the qubits on the composite quantum system. Now, similarly, also this is C naught gate is also called entangled gate, right? So, okay, so there are reasons like Bell state and other things. I'll come slowly how they are important and things are like. Okay, there are certain composites. So in this particular composite quantum system, why gamma and delta positions are changed? I just explained, right? So with these four bases, this is your representation: alpha, beta, gamma, and delta, right? And this will be your, now your basis change, like the information 1 0 will become 1 1, and 1 1 will become 1 0. So just earlier in front of 1 0, what was the coefficients gamma? Now in front of 1 0, what is the coefficients? It will be so basically just like because it has become 1 1, right? And it has become 1 0. So you just simplify the equation and write it. It's a like class 2 level thing. Okay. Now so that's why there is a definition of C naught in this way. So in the measurement operator form, yesterday we have learned it, like how to, by completeness relation, how to write the measurement equation form of certain quantum operator or gates. So CNAT can be represented also as 0 0 outer product, right? This is a like a projector operator, right? Tensor product with I. So because it's a 2 qubit gate, so you have this outer product of 0 0 state will be 2 cross 2 matrix times another identity on the. So basically when you are projecting on the 0 state, it does nothing, identity matrix. But the 1 1 state, right? The outer product of 1 1, when you are getting the result in the 1 basis, right? So there is a NOT operation. So controlled NOT operation. So this is the tensor product, right? So the definition is 0 0 outer product, tensor product with identity matrix, and 1 1 outer product, tensor product with the NOT gate, poly NOT gate. Okay, this is basically equals to 0 1 1 0, right? So this is the definition of C NOT gate in this particular form. Control to NOT representation in the outer product form or the tensor product form. And this is one particular quantum gate, and it looks like this. So if you say start with 2 qubits, get 0 0, right? And it can be 0 0 1 1, whatever it is, but the operators looks like this. Okay, this is the C naught gate representation. Okay. Now let's see another entangled 2 qubit gate or the controlled 2 qubit gate. So I hope somebody, I mean, in QT-05 and other QTs, it is already much detailed described of this kind of gates and all. We are only considering the information theoretic part because that is required to define quantum channel, various channels and all. And you will see, although in 2 hours, it is not possible to cover everything like the entangled channel, breaking entangled channel, those things are beyond the scope of today's class, but I'll give some, at least the topic names and also that in future you can dig those topics. So, so similarly, here I have applied the NOT operation on the second qubit if the first qubit is 1. Similarly, there is an operator called a controlled U operator. Now, one can ask me why we are studying this thing. So these are the language of quantum computing. Like when you are doing classical computation or communications, every logic you try to define in terms of the logic gates, flip-flops, all those things. In quantum, because your language is not Boolean, your language is linear algebra. So you need to understand all the operators that you can perform either directly or on the composite system or in the controlled fashion or uncontrolled fashions. All those operators we need to understand. And those operators, which are typically the unitary operators that to represent on a quantum computer, right? So whether it is photonic or whether it is superconducting, that's a different ballgame. But altogether, the purpose is to find what are those logical operations or the matrix operations that I can perform on a qubit, either a single qubit or multiple qubit in controlled fashion or uncontrolled fashion. Okay, so there is a controlled U gate, and the purpose is it looks like this. So you can here you can have an input state and here you can have an output state, right? This side is output state and here this side is the input state. Maybe you can start with 0, 0 or any other quantum state, but it looks like this. So there is a dot here because this qubit is working as a controlled, whether this is 0 or 1, based on that it will perform the operations here, right? So so the unitary operator, the purpose is if the first qubit is 0, it does nothing. It does nothing. If the first qubit, so if it is, I mean, the first qubit is 0, then in the second qubit, it does nothing. So you can think like this. If it is 0, 0, say for example, it does nothing. It will remain 0, 0. Okay. But if it is, say, 1, 0 or 1 something, say the first state is 1 and the second state is psi. For example, this is a composite quantum system, right? And you apply the controlled U operator. So if you apply the CU operator, controlled U operator, so the first qubit will be as it is, and the second, in front of the second qubit, there will be a like a product with a unitary operator, right? So U times psi, right? So what is the definitions for this? The definition for this is given by CU operator equals to 0, 0 outer product, tensor product with identity. It does nothing if the first qubit is 0, plus 1, 1 outer product, tensor product with the state psi. I shared the yesterday material with Professor Pillai sir. It will be uploaded today, I hope. Don't worry. And today, whatever I'm teaching, I'll also share by today itself. So you will be getting all the notes. So yeah, so please follow the lecture because it's a pen and paper thing. I'm trying to explain each and every things from very basic. So that will be more helpful. And of course, all the notes and everything will be shared. So now we know that how to control, even there is a composite quantum system, still we can control certain qubits and we can perform certain operations on some qubits, right? So, so I made a mistake. It will be U, okay? So this is the controlled U definition, right? So now we yesterday we have learned about the noisy states, right? So the ensembles of noisy states given by its probability mass functions or the probabilities and the associated quantum states, right? These were our representation because there may be uncertainty in preparing a quantum state. Let's collect all the states, see the probabilities of those individual states, and make a set of state and its probability, right? So, and also we have defined something called a density matrix. I'm just repeating some of the things to go to the next topic so that you do not need to remember everything. So for all such I, probability I and the outer product of the states, right? So if you see this equation, this is also sometimes called the expected density operator, right? Because if you know the probability mass function, if you know the random variable itself, so this together is forming a random matrix, and the sum of the probability mass function associated with the quantities that define the random matrix. So it's also called the expected density operator or the expectation over the variable x, random variable x. and the outer product of psi x and x, right? This is another way of thinking the density operator, right? From the probability side, right? So now there is some more properties of the more properties. So is there any doubt, like unable to view the slides? I hope it should be slide in the ensemble probability sum is probability of the state occurring. You can say C0 gate is a special case of CU gate, of course. Acha, there are some more questions. Let me read the questions. U is an unitary, any arbitrary unitary operator, correct. Then Pauli spin operators are also unitary operators, perfect. Then C0 gate is a special case of U gate, correct. In the ensemble probability term S of the state occurring, probability terms, this question is not clear, unable to view the slide. Please rejoin, I hope it is visible. Okay. So now there are some more properties of this density operator rho. So one of them is called the spectral decomposition of rho because it's a Hermitian operator. So it has a spectral decomposition. So because rho equals to rho dagger, trace of rho equals to 1 and x rho x greater equals to 0, it's positive semi-definite. So we of course should get a spectral decomposition of rho, the matrix. So every density operator rho has a spectral decomposition in terms of eigenstates in terms of eigenstates. So assume it has certain eigenstate, and the set of eigenstate is represented by phi x gate. Okay, for some x belongs to some say 0 to d minus 1, this many numbers. Okay. So we can write the spectral decomposition as rho equals to sum of lambda x, it's psi x, psi x, that's outer product of psi x and psi x. These are the eigenbases for over x, right? Where lambda x are the eigenvalues, right? Lambda x are the eigenvalues. So this is important because if you know the density matrix, even all your noisy observations, and this lambda x is important, you check the values of all such real lambda values. Specifically, it's a Hermitian matrix, so all these lambda are real, right? So they are the real quantity. And if they are the real quantity, you check the quantities whether they basically lesser equals to 1 or not. They are between 0 to 1 or not. So if it is more than 1, so basically there is invalid or illegal quantum state. So there is a lot of study from this row onwards. Okay. So I am not going that direction, and the study is called tomography. So those who are interested in quantum measurement techniques and research towards that direction, they can start from this point. Like depending on the various values of lambda, so you try to define various strategies of measurement, new measurement scheme with various eigenbases. Okay, so which is the best eigenbasis say to represent your quantum information and all. So like various types of state tomography and other things are there. So I'm not going that direction, but here is a scope of doing improvement in this angle. Okay. Now let me give you one MCQ question or MSQ question, multiple correct answer question. It's a very easy question just to make you motivated. So a maximally mixed state is given by four options are here. First one is the maximally mixed density matrix of the maximally mixed state. It just you just apply the uniform probability distribution, you will get the answer. The first one is 1 by d summation over I, ket I, ket I. Second is identity matrix by D. Third option is identity matrix. Fourth option is all of this. So, so this is a multiple correct answer question. So what are the answers? Can you just try and apply it? Everybody answer please one time, right? Somebody is answering A, B, C, D, all this. Please apply only one person, one option. Okay. So I'm giving, in fact, 1 minute to solve this problem. So by definitions, you know these things like the definitions of this one, right? The density matrix and the probability distribution for maximally state is the uniform distributions, right? Uniform distribution gives you the maximal probability. Like for example, superposition is half half. If there are four state, it is one fourth, one fourth, one fourth, and one fourth, four state. So similarly, just apply it here. Just a 2-line question, and let me know the answer. Yeah, the answer will be 1 and 2, both 1 and 2. Okay, both 1 and 2 are correct. Okay. So now slowly we'll go towards channel, but even before that, there is something called a noiseless evolution, and then we'll go to noisy evolutions, right? And then we'll learn some more things. No cloning theorem and all we'll visit, don't worry. So let me connect what are the things yesterday we covered with today's thing. So first is the noiseless evolution. Right. Yeah, some of the things I'm not giving proof for the sake of time. The proof are standard, just either reference book like the Nielsen Chuang or the Mark M. Wilde, or in fact, John Pascal's lecture series, if you see, or his book, if you see. So there are all the proofs and everything are there. So some of the important facts only I'm sharing, and these are important to understand quantum communication from information theoretic way. Okay. So noiseless evolution, if we see, so it's like suppose we have some input state that is ket psi x, and it passes through an evolution matrix U, and we get psi y, for example, where psi y is your U times this psi x in the state vector representations, right? So suppose so noise can be where here you can have noise, but I'm saying noiseless evolution means there is no noise in the evolution path. That means in the channel part there is so you learn the communication channel, right? You have transmitted a signal, it passes through wireless or fiber optical channel, certain channel, and you get an information back y. X can be your random variable, y can be your random variable. Your channel can bring randomness because of lots of variability factor, refraction, freeze equations and all, right? Absorptions, everything, all the phenomena are there, right? So signal attenuations, and your hardware at the receiver also can bring uncertainty due to hardware impairments, various thermal noise and all. So, but for the time being, assume that this U is very good. There is no problem in the quantum channel versus the classical channel. This is very ideal channel, right? And you have only uncertainty in X. and we can represent the evolution ensemble as px of x and u of this psi x, right? Because it is initially you had the ensembles as your probability of x psi x, and the evolution you have the probability of x is the only randomness coming in this psi x, but not in the evolution. So the evolved state is just u times the initial state, u times the psi x, right? So now if that is the case, then we can write the evolution density matrix rho evolution evolved equals to just by definition summation over x p of x, that is the probability mass function, and we just defining it with the outer probability, this one evolved state probability, that is u psi x, right? Outer product psi x times u dagger, right? So it's like this one is like y dagger state, right? This state, outer probabilities in the Ket notation you can see as outer product, right? So this u is there is no noise in u, so you can keep this u out of the summation term, and we can write it as summation over x p of x times this, the randomness is here, and the associated probability is here. So outer product of psi x times psi x, and let make this u dagger outside the summation term. So this is the perfect definition of your initial this density matrix, right? So the evolved density matrix we can write as u rho initial density matrix times u dagger, and this is a very important equation for evolved quantum state in the density matrix form, assuming there is no noise in the quantum channel, right? So this is, I hope there is no doubt. If you have any question, I can repeat the portion. So this is the evolution, like it is equivalent to write something like that. You have an initial quantum state density matrix, it's passing through a quantum channel without any noise, and you are getting rho evolution, right? And this is the equation for this. So here it is equals to u rho initial u dagger. It has a good relation with something called POVM operator. POVM operator. So measurement, we have yesterday introduced what is various measurement operators in the outer product form, right? Using the completeness relationship. So so those set of operators are called the POVM operator or positive. Let me write, those who are new, it will help them. So positive operator valued measurement. In short, we call POVM, right? A positive valued of positive operator valued measurement POVM is a set of operators that satisfies non-negativity and completeness properties. Right. So that means if I have a set of measurement operators, lambda j, for example, so they has to be non-negativity means positive semi-definite, you can say, right? So basically lambda j greater equals to 0. And also sum of this lambda j should be equals to identity matrix, right? So yesterday we have seen like we could because the identity matrix we could represent in this way, right? If 0 is the computational basis, right? So we have seen that we can write at 0 0 plus 1 1 these are the projectors, right? Pi 0 plus pi 1, here it is, right? This is pi 0 operator and this is pi 1 operator, measurement operator. Similarly, we could also see like we can write it as plus 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 minus minus as an outer product, right? This form also, where my measurement operator are the superposition basis. Here my measurement operators are the computational basis, right? So these are basically we can check whether these two matrices are following this definition like non-negativity and completeness. So of course they are following the completeness relation, and individually you can also check whether they are greater or equals to 0 or not. Then you can say these sets of measurement operators are called the POVM operators. Okay. Now given a POVM operator, we can find a particular state, whether the quantum state is in a suppose suppose I have a quantum state psi, right? Is a quantum state. So I can calculate the probability using the POVM operator. So the probability of obtaining the quantum state in say J basis. Okay. So you can find is given by the psi lambda j. Lambda j is the corresponding POVM operator and psi. Right. So this is another way of writing or measuring the probability of the state is in the psi states. It's just like expectation representation. Given that the state is a pure state, given a pure state. Pure state means so basically there is a certainty in the state psi. That means you do not have an ensembled representations, right? So P0 and P1 are POVM operators, right? You just take it like so. This kid P0, pi 0 and pi 1 are POVM operators, correct? So we just check the definition, whether they are individually PSD matrix or not, like they are non-negative matrices, and also just check that their sum is identity. Of course, their sum is identity. This property I just directly validated. This property you take any individual vector like unit vector. For example, you take ket 0 and you multiply with this and check whether it is giving positive or 0 result or not. If it is giving you negative result, then it's not a POVM operator, right? So you take any unit vector. So what we need to do, x rho x, this multiplication should be greater equals to 0, right? Here also you need to do if you want to call pi 0 as a POVM operator or not, you just need to do like these things. So 0, pi 0 and 0. This quantity, we just check whether it is negative or not. If it is non-negative, then it is satisfying the POVM definition. Of course, I have taken pi 0 from the completeness definition, right? So now the probability of obtaining the quantum state in the J is given by this particular definition, like just expectation pi lambda J and pi, right? So given a pure state, given a pure state kit size, right? So this is one way. But there is a different or another interesting definition of finding the probability. We can also find the probability in state ket J given by trace of lambda J times rho. So lambda J is my POVM, particular POVM operator corresponding to the basis ket J, right? If I know that, then the calculating this quantity and calculating this quantity is the same quantity. It's the trace of lambda J times rho, right? If the state, so this formula will be using if the state is in a mixed state, or if the quantum state, in fact, I can say is in a mixed state described by some density operator rho. So if it is a mixed state, we can, in fact, those who basically are familiar with linear algebra, you know that trace of an operator is the inner product, these relations, right? So they are also obvious from the linear algebra equations. You can always check, right? If you have two matrix A and B, then also trace of this, you can also write it in this form, inner product form. I'm not giving the proof because of lack of time, so skipping that part. So this is this way of writing the probability, that probability of a particular state Pj equals to trace of lambda j rho. This is also we are reformulated the representation for Bond rule, that yesterday we have seen the Bond rule for quantum measurement. So for example, to measure the quantum state in the zeroth state, right? So by that we have seen like the zero inner product with psi, right? It will give you the probability of the state zero, projected value in the state zero, psi in the state zero, right? So that Bond rule becomes now this one for the mixed state, lambda j times rho. The same thing. It's a different way of representing the information, right? Now, so now we'll start the noisy evolution and the impact of environment slowly. So I'm giving a 5-6 minutes breaks here, and we'll continue after the break for this part, like the quantum, the noisy quantum evolution and implication, specifically the this thing, the no cloning theorem, etc. Okay. So we'll come back in 5-6 minutes.